Hello, it's Keith here, and this is lesson 3 of my SuperH assembly programming tutorials. We're going to be continuing looking at the SuperH programming language, assembly language. Now, what we're going to do today is we're going to look at the conditions, how the T flag works, the false true condition flag. We're also going to have a recap of the stack. We've covered it briefly before, but we're going to have another look at it today, learn how to use that. So we've got a few things that we're going to do. Let's go over to our source code and let's take a peek. Okay, so we're on lesson 3, so we're looking at lesson3.asm, and as with the other lessons assembly files, we have a piece of code at the start, and what this does is we've got branches to the various sections of today's lesson. So first of all, we're going to look at the false or true, and we're just going to understand how the T flag works with regard to conditions. Okay, so this is the section we've got. Let's compile this. This should work on either, but let's run it on the 32X. So we're going to assemble this on the 32X, and the first thing we're going to discuss is the commands set T and clear T. Now the T flag is a single bit flag. It's actually one of the bits of the status register, the least significant bit there. So this is basically in this case used as a false and a true. So we can basically set this via conditions, but we can also basically force it to have a value, which is quite convenient for our testing purposes because we don't need to worry about the conditions. We can literally give it a value and then check what happens is what we expect it to. So we've got the command set T, which will set the T flag to 1. We've got clear T, which will clear the T flag to 0. And we also have another command, which is move T, which will actually move the T flag and only that one bit into a register we specify. So here we are basically moving the T flag into R0 here. Now there's no reverse of this command, so we can't move a register back into the T flag, but I mean, it's not necessarily clear to me why we need this command at all. It's very handy for us doing testing, but as I say, yeah, when we've got branches that we can do based on the T flag, why would we want to move the T flag into a register in its own right? But it could be useful for some of the rotation commands maybe. Anyway, as I say, very handy for our testing. So here we've got a set of the T flag and then a clear of the T flag, and then we're moving the T flag into R0. So when we show the registers to the screen, it shouldn't surprise us too much that R0 contains 0 because we last cleared the T flag. Now, my monitor is actually showing the T flag to the screen there at the end of the screen anyway, so we can see that it was false, 0, as we can see there. But we are then also basically going to do some conditions anyway, and we're showing an F or a T after that line as well. So basically, here we cleared the T flag before showing the results to the screen, but this time what we're going to do is we're going to disable that clear command here, and we're going to run this code again just to confirm that that set command is indeed setting the T flag. So we've run again, and this time you can see that the R register after that move contains 1. The T flag is being shown as set here, and then we're showing the T after that as well. Now, as I say, my monitor is showing the T flag to the screen, but we've actually got similar code here that is actually responding to the T flag and branching accordingly. So what we've got here is we've got a command here to move a letter T into R0, and then we've got this BT command. And now this is nothing to do with the UK British Telecom. This is branch if true. Now this is a branch and it's using the T flag, and if the T flag contains 1, then that is considered to be true. So we're branching to a do print char after that line. However, after that line, we're loading an F into R0, and we've got BF, which is branch if false. So we've got these two branches here, and unlike our usual branches, branch to subroutine here and the like, you'll notice that there's no op after this. And my colouring here has done this in red and these in pink, and the pink is supposed to denote something with a delay slot. Branch if true and branch if false, a little bit surprisingly, don't have a delay slot, which maybe makes things a little bit easier for us. So we don't need a no up there, and these commands will be loaded before the branch. So we are showing a T to the screen if it's true, and you saw before we were showing an F to the screen because only one of these will occur. Now we've got a third option here, which is going to load a minus to the R0 and show that to the screen. However, the T flag is either set or clear, so there's not actually any way for that to occur unless we actually sort of set the T flag in between these two. If we run this again now, because we've cleared the T flag here, then this condition isn't true, but then we've set the T flag here, so this condition isn't true either, and so now we get that minus. And as I said before, the intention is you download these and have a play with them and rem out and enable different options and change conditions and things so that you can ensure that you understand how these work and confirm that my code is doing what I'm saying it is, if nothing else. So that's how we can use BT and BF to do simple branches, and obviously in this case we've just hard forced the T flag to be set or clear, but we will later on see various ways of setting it. Now this BT and BF can actually be used as part of a loop, and this is of course very handy. A lot of assembly languages have loop commands like DBRA or the DBNZ commands in Z80 and 68000. The SuperH has a similar command. So what we're going to do here is we're going to use decrement and test here. Now this will basically decrement R0 and then it will test it and set the T flag accordingly. So what we're going to do is we're going to load R0 with the value 4 here. We are going to load R1 with the value of 0 here, and we're going to do that because we're going to repeatedly add 2 to R1. So we'll be able to see how many times this loop actually occurred until the decrement and test caused the breakout. Now DT here is decreasing the value in R0 and it's setting the T flag, but it doesn't actually perform the branch. We need to perform the branch to jump back to the start of our code when R0 hasn't reached 0. Now the T flag will be set when R0 reaches 0. So we want to do a branch if false here to make this loop repeat until R0 reaches 0. So let's run this and let's see what happens. Okay, so at the start of our run, R0 contains 4, R0 is our loop counter, and R1 is 0. R0 is our test value. And then we're going to repeatedly add 2 to R0. So you can see R0 goes 2, 4, 6, 8. Now R4 goes 4, 3, 2, 1, and then 0. Now on this last iteration, when R0 reached 0, that is the end of the loop here. Because you can see we did our decrement and test, we ran the monitor routine which doesn't change the T flag, and then we repeat if the T flag is not set. Now you can see here the T flag is being shown on each line, and that last iteration the T flag was true, and so the branch if false did not occur. So that's how we can use branch if false to create a loop using a register, in this case R0. So a very convenient command there. That's going to be something handy to have. Now in all of these cases, branch if false and branch if true do not have a delay slot, which for someone like me used to the humble Z80 and 68000, delay slots are a little bit of a pain. But of course there's no denying that they are, if you're trying to do efficient coding, a handy thing to have, because if you manage to put a command into the delay slot, then that means that you've saved a little bit of the processor's time, because the processor has to flush its instruction pipeline. It's always reading a few commands ahead, and if it turns out it has to branch, it has to clear out those commands it's already read and maybe started processing, so that causes a little bit of slowdown. So the delay slot allows us to use those commands, but it does make the programming a little bit more confusing for the programmer reading it maybe. But as I say, BT and BF do not have a delay slot. However, there is an alternative version. It's BT/S and BF/S, and the S represents a delay slot here. So these are the versions with the delay slot. And what we're doing here is we are recreating this code here, but this time we're setting the R0 to T or F in the delay slot of the branch. Now this will effectively have the exact same function as before, but if we were super tight on our timing, it would be very slightly faster. So in this case, what we've done is we've cleared the T flag here. So what we've done in this case is we've cleared the T flag here. Here we are going to branch if true to do print char, and although this command is after do print char 2 here, it's actually going to be executed before because it's in the delay slot, and BT/S has a delay slot. This also will set the F before the branch, and BF/S will occur in this case because we have cleared the T flag up here. And you can see here we've shown that F to the screen there because that has indeed happened. So say the loading of F there has occurred before the branch because of that delay slot. Now if we just change this and run again, we set the T flag here this time, and so this time this line will occur and the T flag has been set here. So you can see that has indeed worked. Now if we were to change these to BT and BF, well, now there is no delay slot, and so we actually get some garbage to the screen because who knows what's in R0. It's not that T because it will be something as a result of our loop counters up there. So we do need to make sure we know what we're doing here. So as I say, that's how we can use the true and false and do simple branches based on the T flag. Now what we're going to do next is we're going to look at some compares. So compares are basically how we do comparisons between two values. So if we've got a value in our registers and we want to see which is higher or lower, or if they're the same, we can do that. And of course we're going to need to do this an awful lot. If our player's moving around the screen, we want to make sure they don't go over the screen. We need to bounce them back. If our player's lost a life, have their lives reached 0? If their score's gone up, have they got a new life? That kind of thing. And of course that's just gaming. It's going to be every kind of application is going to need to do comparisons, to do all kinds of things. So what we're going to do is we're going to load a couple of test values. We're going to load in R0 with a value, in this case 0, and R1 with a value, in this case 2, and we're going to do some comparisons. Now the kind of comparison we're going to want to do is going to depend if these values are to be considered signed or unsigned. Now in low values like this, it doesn't really matter because it's not going to make any difference anyway, but for very high or negative values, it is extremely important. So we've got a variety of options here. You can see they're all remmed out with the exception of one. Now again, what I would suggest you do is download these and try all kinds of values and just check they work and check you understand how they work. I'm going to show you a couple here, but you know, how many you need to do depends on how easy you find this to understand, and I've sometimes got confused with regards to negatives and positives and things, and trying it out yourself certainly helped. Now the compare command on this system, basically we do a CMP and then there's a slash and then there is some kind of code, in this case HI, which is the equivalent of higher, and higher refers to an unsigned comparison. GT is greater than, and that is for a signed comparison, so it does make a difference here. So we're comparing R0 to R1, and what this will basically do is it will set the true flag if R1 is greater than R0 here. So we've then got a branch, and we're branching to a subroutine called print GT. These are just simple routines I've written that will show various kinds of characters to the screen so we can see what the result of our branch was. Now in the case that we've got here, R1 is 2 and R0 is 0 here. So if we run this now, well, our comparison is occurring, and R1 is greater than R0, so the greater symbol has been shown. So that has worked as we would expect. Now if we change this value here and we load R0 with a value of 4 and we run again, well, this time when we run, this condition isn't true, so this branch if true does not occur. Now we've got no branch if lower here, so what happens is we actually continue in our execution here until we get to this loading of the X symbol here. So we've shown an X there, and so that means effectively that basically the value is either lower or the same. Now we can do a comparison for equals with CMP EQ here. That will do a comparison if the two are the same. Now we can change these here and we can set them both to be the same and just confirm that does work. And so you can see we've got equals there. Now, as I often say, if you want to see the full range of commands available, you can download my cheat sheet and you can print it out if you wish, or you can just view it. Yeah, you can see it's a little bit small on the screen here, but basically it's got all of the commands, and you'll notice that there were some absences really. I mean, we've pretty much shown all of the commands here in our example here. Now you'll notice in that list there was no command for less than, but what we can actually do is do that in reverse. We can simply compare and see if the value is higher than or the same, and then we can do a branch if false, because by definition if the T flag is not set, the value must be lower. So that's why we've only got highers and not lowers in these comparisons. We simply don't need the opposite version. Now what we're going to do next is we're going to try a new value. What I'm going to do is I'm going to set a value of -1. Now -1 is obviously lower than 2. So let's so we would assume this branch won't occur and this branch won't occur. Let's fire it up and let's see what happens. Well, that's a bit of a surprise. The branch has occurred and it seems to claim that R1 is actually greater than R0, because that doesn't make any sense really if you think about it, because R1 is -1, but I've made an intentional mistake. You see, the compare higher command is working with unsigned numbers. Now -1 in hexadecimal, if we just get our calculator up, if we show the calculator and I type in -1 here, -1 in hexadecimal is actually a large number of F's, and if that was an unsigned number, that would basically be a huge number that reached the absolute limit of the register. So depending on whether we're treating our registers as signed or unsigned, that's either a very large number or a small number, and we've used the wrong command here. We've compared with an unsigned higher, but what we wanted to do is we wanted to use the signed version, and so what we need to do is use this version, GT, rather than HI, and this is actually going to treat the number as signed. So basically, if we run this, well, the value is of R1 is lower if it's considered signed, and so this time the branch has not occurred and the X has been shown there. And of course we can now test this by setting a different value here. If we set R0 to -2 and run again, well, this time R1 is -1 and R2 is -2, so R1 is greater than R0 because it's less small, and so the branch has once again occurred. So we do need to make sure we're using the right comparisons for our values. Now, in addition to comparing if higher than and if equal to, we can also do a few other comparisons. We've got a branch comparison if plus and a comparison if 0, and so these are for checking if our numbers are signed. Now, of course, these don't take two numbers, these only take a single one. So if we run this here with a value of 2, this is a positive number, so we get shown greater than 0 here. And if we change the value to 0 here, well, this isn't a positive number, it's a 0 number, so basically we will now not branch away. We do have an alternate version. If we want to check if a value is negative, we can do compare if plus or 0, and in this case we will branch away because the value is greater than or equal to 0. So if you want to basically find your negative numbers, you can use that. Now, we do have one special case. If we are using the R0 register as our value that we want to compare, we can actually compare a small immediate value. So in this case, we are going to compare R0 to the immediate value 1 here. And so if we just set R0 to 1 here and we run again, well, in this case, we've compared R0 to 1, and R0 doesn't contain 1, so the branch has occurred, and we've shown an equal sign. But of course, if we change this to 4, then we can run this again, and now it, of course, does not. Now, this is a small value only, so we can do a value of 127, and we can compile that. That will work. But if we do a value of 128, and we try and assemble this, well, we've got an addressing mode not allowed error here, which basically means that won't fit into a single signed byte, which is the limit of this command. As I say, we've got a wide variety of options here, and depending on whether you use BT or BF, they will have different results, and as I say, it can get a little bit confusing with signed and unsigned numbers. So what I suggest is you download this example and the build script and try it out yourself if you want to spend more time understanding how these work. But I think generally speaking, if you're writing your own little programs, I think necessity will help you understand which ones you need to use, because you will want to do things. You will think, how do I do this? And then you will start to realize, well, in this case, I need to use this command to get the result I need. Now, we've looked at numeric comparisons here, but there is one slightly strange command here, which is again, it's one of these ones that I don't immediately see the use for, but it's an interesting command and definitely worth discussing. Now, we've got this command cmpstr. Now, this str refers to a string, and the word string has various meanings on various different systems. Sometimes it means a series of bytes, but in this case, what it's doing is it's comparing all the entries within a 32-bit register value, and it's seeing if any of the entries match. So if any byte within this register is in the same position in this register, a match will occur. Now, in this case, you can see that the second byte from the left there is 22 in both cases. So when we do our comparison here, the T flag is set, and the branch it will go to this routine, which simply shows the word into the screen. You can see the T flag has been set here. Now, that has occurred because of this value 22 in the same position in both cases. But here's the thing that surprised me when I ran this command at first. Now what I've done here is I've moved the value 22. Now the value 22 is in both registers, but is now not in the same position. It's not in the same byte position in that 32-bit value. So this time the condition has not set the T flag. Actually, there's a mistake in my code here. I just need to move this up here to set the T flag correctly before we do the branch. So in this case, the T flag has been set to F here, and so the branch has not occurred because, as I say, it's not just that the value 22 needs to appear in some position, it needs to be in the same position. If we replace this FF, and my mouse stops sneaking away there, and we run again, so we put a 1-1 there. Well, now the value 1-1 is in the same position in both, so the T flag has been set. A very strange command to me. I can't initially think of why you would want this. As the 8086 has commands that process large strings of data, but this seems to work with just a single register's 32-bit value. I guess there may be cases you want to do a short comparison of byte data, but I couldn't initially think of a reason I would want to use this. But I'm always happy to see commands that have a lot of potential to them, so definitely worth discussing, and I'm sure you can think of lots of far smarter ways of using it than I can. Anyway, that's all we're going to do on comparisons. We're going to now move on to the stack. We have discussed the stack a little bit before, but we're going to go into it again and just see some examples here. So what is the stack? Well, as I always describe the stack is a bit like an in-tray. If you've got too much work to do, people keep giving you work. You've already got one job to do, and then someone gives you a second job. So you can't deal with your first job. You put it into your in-tray. You start working on the second job. The second job gets interrupted by a third job. So you put the second job into your in-tray and you work on the third job. When you finish the third job, you take that job away, and then you take the job out of your in-tray and start working on again, which is the second job. And then once you finish that, you take the original job out, the first job. Now that would be referred to as last in, first out. When you take something out, it's the last one you put in. And that's the way the stack works on basically all systems as far as I'm aware. So we basically put things onto our stack, and the stack pointer will move down in memory as it does. And when we take them off, we get them out in the reverse order we put them in. Okay, so what we're going to do here is we're going to use register R12 just so we can see the stack, and then we're going to load some test values into registers 6, 7 and 8 here, and we're going to run this routine which will show the contents of the stack so that we can see what is actually going on in memory. Now my subroutines themselves will actually change the stack, so you might see entries that are removed from the stack disappear, but that's not a function of the processor, that's the function of my test code, so just bear that in mind. Now we've loaded the values -1, 2 and 3 here into registers R6, 7 and 8, and then we've run this monitor stack function. Now -1, 2 and 3 basically look like this. You can see these very large values here. These are negative -1, 2 and 3. Now what we're going to do next is we're going to move R6 onto the stack, R7 onto the stack and R8 onto the stack here. And so basically this was the original state of the stack here, and then you can see these values here. That quadruple F there is -1, that 6 Fs and then FE there, that's -2, and that's -3 there. So they've all gone onto the stack there, and they've gone on in descending order. So the -1 was pushed on first, and that has appeared here, and then -2 has gone on, and that has appeared lower down in memory here, and then -3 has gone on, and that has appeared last, if you will, here. And the reason that they've gone down in memory is simply the command we've used. We've said move the register onto the stack pointer and decrement the stack pointer first before moving the value. And of course the stack pointer is effectively register R15 on this system. So that's what we've done here. So we've effectively backed up registers R6, R7 and R8 onto the stack. We've then loaded in new positive values into our registers. So we've loaded 1, 2 and 3 here, and you can see 1, 2 and 3 here. and our original negative values are on the stack here. But the point in most cases of the stack pointer is to allow us to do short-term work and then get old values back again. So our short-term work here was to load positive values and show them to the screen, but now we want those old values back. Now we pushed our 6, 7 and 8 onto the stack. Now these were values -1, -2 and -3. But when we restore them off the stack, we're going to get them in reverse order. So we're going to get -3 first, -2 second and -1 third. Now -1 we're going to load into R6, but just to make the point, the value that we pushed on in R8 we're going to load back into R7, and the value that we loaded onto the stack in R7 we're going to get back in R8. Now the reason we're doing this is just to make the point that the value we pushed onto the stack, it doesn't matter what register it came from, the register it goes into simply depends on the order that we pop them back off the stack. And as I say, it's last in first out, so the -3 that we pushed on last will be the first value that we pop off. So when we've restored these and we've shown the results again, well, this time R6 contains the same value, FFFF, all F's there, but the value in R8 that was that FD, that -3 there, has now ended up in R7 FD there, and the value in R7 has ended up in R8 here because we've used the registers in the reverse order. Now if we wanted to do this correctly, if that wasn't what we intended to do, we need to make sure we obey the last in first out rule. So we pushed R8 onto the stack here. If we want that value to end up back in R8, we need to pop R8 off the stack first. At SP plus is of course popping off the stack, load from the address in the stack pointer and increment the stack pointer after the load. The minus before means pre-decrement. The plus afterwards means post-increment. So when we run this again now, if we run this, you will see that R6, 7 and 8 contain the exact same values in the exact same order afterwards, because we have correctly, if that was our intent, popped them in the same order as we pushed them on. There we go. Now that is one common use of the stack here. Now another very important use of the stack on this processor, on most processors, is with regards to subroutines. Now some processors actually push the return address onto the stack as a default function of the call to subroutine. The Z80 does that, a lot of other ones do. However, if you're not nesting subroutines, there isn't actually a need to do that. So some processors, the RISC processors, often don't do that, and that's true of the SuperH. So if we want to call a subroutine, and we definitely do in my examples because I'm using these subroutines like monitor stack, well, that will actually change our return address. Now on the SuperH, our return address is loaded into a special register called the PR, the procedure register. So this will contain the return address when we jump to our subroutine, branch of subroutine subtest. So the return address would be then loaded into the PR. However, if I call my subroutine monitor stack here, that value in the PR register would be lost by that extra subroutine call. So we want to back it up somewhere, and what we're going to do is we're going to back it up onto the stack pointer. Now regular registers we can just back up with a move command. However, the special registers like that, the PR, we need to use the STS command, which is for storing system registers. So what we're doing here is we are moving the PR register onto the stack. We're then moving R6 onto the stack. We're then running our monitor function here. And I've made a typo here. This should be R6 and R6 here. I apologize. I'm copying and pasting things and not changing them. So here we've backed up R6 and here we've restored R6, just as an example here. And we're showing the contents of our registers here. Now, if we run this here, you will see we've run our code. Now, I've actually done a trick here. What I've done is I've loaded return pos into R7 before we've run this subroutine here. And that is just to make a point. Now, R7 is effectively the return address after this subroutine. And so what I'm showing here is the value that I know the PR register will contain when this subroutine executes. So we've done our monitor of the stack here, and you can see here is the stack. This value here is the value in R6, and that just allows us to see there's a value before that, and the value before that is 06000180. Well, what is that? Well, coincidentally, it's the value in R7, and it is, of course, the value in the PR register, the return address that we need to have to get back to the code that called us. Now, that is a viable subroutine that allows for nesting. Now, if I change this code and I remove these lines here and I run again, well, now we've got nothing on the screen, and what's simply happened is that this subroutine has corrupted the return address, and the return is never occurring. The return is probably actually creating an infinite loop, because the return address will be the return of this monitor stack here. It's probably repeatedly popping infinite values off the stack and never actually getting back to the calling code. Now, if I change this code and I remove this branch to subroutine here, well, now you can see everything works fine again. And the reason this works okay now is we're simply never calling a subroutine. It's not that we need to back up and restore the PR register. It's that we need to back up and restore the PR register if we are nesting our subroutines. And so that's why RISC systems often don't back up the return address onto the stack. They load it into another register, because if you are not nesting, it's a waste of processing power to be using the stack. But if you are nesting, you need to back up and restore the PR register. And I'd suggest as a beginner, always back up the PR register and restore it, because you're going to find, you know, sometimes you'll think, oh, I don't need to nest within this subroutine, and then later on you will, and you might forget. So if you're not worried about speed, it's going to be easiest for you to just get used to maybe making a macro that you run at the start and end of your subroutines, just to clear up any potential mess like that. We're going to discuss briefly in macros that I use in just a moment. But one thing we're going to do now is we've basically seen STS there, but we're going to see some other options with regards to that. So we have special kinds of register on our processor. We have the general purpose registers that are just numbered R0 to R15. R15 and SP are of course the same thing, but we have some special registers. We have SR, GBR, VBR, MAC-H, MAC-L, PR, PC, and depending on the processor you may have a few others, but those don't exist on the one we're looking at today. So how do we actually work with those registers? Well, we have special commands to load and store them. We have LDS and STS for the system registers, and LDC and STC for the control registers. Well, what is defined as a system and a control register? Well, basically a system register is the MAC-H and the MAC-L and the PR. MAC-H and MAC-L are for multiplication. We will see those in a later lesson. The control registers are SR and GBR and VBR. Now, VBR is the vector base register, GBR is the global base register, and SR is the flags basically. Now, the important thing to understand is that the control registers are effectively what are referred to as privileged, and this means that you might not be able to access them depending on how your operating system is set up and what processor permissions you have, and also if your operating system is not expecting them to change, you might crash the system with this. Now, the example we're doing here works fine on the 32X. However, if I take this again and I run this on the Saturn, well, the Saturn emulator has actually crashed. The Saturn does not like us messing with some of the control registers. It's actually this one here that I believe the Saturn doesn't like. If I run this line out and I run again, well, now we're in the clear. Our Saturn is happy again. So as I say, it does depend on the system that you're working with, what is allowed. If the system's operating system is using vectors, vector traps, and we mess with the vector base register, we're going to have a pretty bad day there. So as I say, it does depend what system you're using, what you have the potential to do. Although these are things that you probably don't need to do really. You're going to have to work with the procedure register, and if you're doing multiplication, you're going to have to use MAC-H and MAC-L. But these you probably won't need in most cases. I'm doing things with the flags registers to show them to the screen as part of my testing routines in some cases, but if you're actually writing your own little programs, you probably won't need to do that. Now, anyway, in this case, what we're doing is we're loading various test values here, and we're loading 3, 4, and 5 into MAC-H, MAC-L, and PR here. And you can see those here. MAC-H is here, MAC-L is there. The procedure register we can't show because basically it's used as part for the subroutine. It's changed by the execution of the subroutine, but you can take my word for it. We have indeed loaded it there. And here we're loading values into SR, GBR, and VBR. And you can see VB is the VBR here, GB is the GBR here, and SR has been loaded here. So we can load in various values here from registers, but in most cases what we would actually use these for is to back up the special registers onto and off the stack. So what we're doing here is we are backing up the procedure register, the multiplication registers here, and the service register, the GBR and the VBR here, and we're restoring them here. Again, to what extent you need to do these will depend on your code. You might want to back up the multiplication registers if you're doing multiplication in your subroutines. For my testing, my monitor routines, being able to do this kind of command is quite handy as well. So, but as I say, a lot of these are things you probably won't actually need in your code. Now, we've looked at various things that you can do with the stack today, but one thing you might be wondering is, well, what if you want to back up a lot of registers at the same time? And like a lot of other of the RISC systems, the SuperH doesn't really have any commands to do multiple registers at the same time. So if you want to back up all of the registers in one go for simplicity at the start of your subroutines and restore them at the end, you're actually going to have to do that yourself with literally a large sequence of push commands here, moving all these values onto the stack, and pop commands moving these all off the stack. And so what I've done is I've created a macro called push all and a macro called pop all. So these are just very simple, ultra safe routines, and I put these at the start of things like my print char routine. If you were wanting to return a value from your subroutine in one of the registers, obviously you wouldn't want to push them all. I mean, those are my absolute basic ones. What I would tend to do is just use those for ultra safety. If I'm creating a routine that I really don't want to change anything, if I'm writing an actual routine that I know what it's going to change within that subroutine, then I would do it more simply like this and just have a sort of chain of backups and restores for the registers I'm using. But as I say, the SuperH, like other RISC processors, doesn't have a command to back up and restore all or sequences of registers onto the stack and off the stack. So you probably do want to create some macros. Anyway, that's all we've got for today. If you like what we've seen, make sure you've liked and subscribed. We're halfway through the series. If you've not seen the rest, check it out. Go to the website, download the source code, build scripts, try out what you've seen today. That's what it's there for. And we've still got a couple of lessons left, so I hope you're going to stick around and check them out. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.